What we're going to unpack today is how to gain information about stars from a blackbody spectrum. So what I've drawn here is a blackbody spectrum, and we have star A and star B that we are going to compare. Now the first information we can get from a blackbody spectrum is relative temperature. And to get relative temperature, we want to use the wavelength of greatest luminosity. You might also see flux here or energy output, but what is plotted here on the y-axis. So we want to look for where that y-axis for our blackbody spectrum would be the greatest. Now for these two particular stars, the greatest energy output is the same for both of them. So we're going to sort of estimate here. Ideally, if your instructor wanted you to actually do calculations with this, then you would be provided some information on the x-axis. Alright, so the peak wavelength there is in the green range, where over here it's in the red range. So what we have over here is called Wien's law. And it tells us that this peak wavelength, so I've established this peak wavelength is in the green, and this one is in the red, is inversely proportional to the temperature. So if wavelength goes up, temperature goes down. So as wavelength goes up, temperature goes down. If wavelength goes down, temperature goes up. So for our two stars here, we associate over here the left with short wavelengths and the right over here with longer wavelengths. So this is going to be our shorter wavelength, and this is going to be our longer peak wavelength. And this may be a little bit different than you're used to thinking of. When we talk in art or talk in feelings, we usually talk about red as being fiery and hot, and blue being more of a cool kind of watercolor. Well, unfortunately in science, it's the other way around. Red objects are cool, blue objects are hot. So the shorter the wavelength, the hotter the star. So notice here that this matches our rainbow colors. I've written Roy G. Biv across. We usually ignore indigo in science. So these are the same colors across as the rainbow. So if you remember your rainbow colors, you can remember your visible spectrum. So over here we have longer wavelengths. So this means a cooler star. Over here we have shorter wavelengths. So this means a hotter star. Now keep in mind this is just the peak wavelength of the star. And typically when you talk about peak wavelength in the visible range, that tells you what color the star is going to be. But that doesn't mean that's the only wavelength that the star emits at. So it's going to have photons emitted for this star B over here, or a red star, is going to emit a little bit of blue light, a little bit of green light, a little bit of yellow. But most of the photons are going to be over here in the red, which is why you see the star as red. But over here, our peak wavelength is in the green, so we would see this more as a yellowish green star, even though it does emit photons at all these ranges. So it does emit red, orange, yellow photons, but we would see it more at whatever the peak wavelength is. So we'd see this as more of a green-yellow star. Alright, so thus far we've learned that the wavelength of maximum luminosity, flux, energy output, whatever your professor prefers to use, gives us the temperature of the star. So the shorter the peak wavelength, the higher the temperature. The longer the peak wavelength, the lower the temperature. And this is given through Wien's law, and this appears a constant that a professor would give to you and explain what it is if they actually wanted you to do these calculations. The other thing that we can get from a blackbody spectrum is the comparative size of two stars. Now notice here that these two stars have the same luminosity, and I have another relationship written over here. So this is where we can do a lot more comparison here. There's a constant here, which if your professor wanted you to do calculations with, would explain to you. But I want to focus on the comparative nature of this. Luminosity, radius, and temperature are all interrelated. So we've already established that star B is cooler than star A by using those peak wavelengths. And we've noticed by looking at the y-axis over here that the luminosities are the same. So, according to this relationship here, if the luminosity is the same, that means that comparatively, since the temperatures are different, the only way to get the luminosity the same is to have a different radius or a different size for each star. So, looking at this relationship, since the luminosities are the same, we can focus on just the radius and the temperature in this relationship. So, moving radius to the other side, we see that radius is inversely proportional to the temperature. So as the radius goes up, the temperature has to go down, or as the radius goes down, the temperature has to go up. So that means if we know the temperature of A is greater than the temperature of B, that means the radius of A has to be less than the radius of B in order for this relationship to be held true. So when you see stars that have the same peak luminosity but have different surface temperatures, that means their radiuses have to be different. And so temperature and the radius are inversely proportional to each other. Now what happens if we want to hold a different variable constant? So let's draw another star in here. Hopefully everybody can see this yellow. So what happens if I draw a star where instead of the luminosities being the same, the temperature is the same. So we're going to call this star C. Well, now the temperature of A equals the temperature of C. So we're going to focus in on the radius and the luminosity. So here we see that luminosity is directly proportional to size. So as luminosity increases, size increases. As luminosity decreases, the size decreases. So the luminosity of C is greater than the luminosity of A. So that tells us that the radius of C is greater than the radius of A. Now, in order to use this relationship we just learned, one value has to be the same for both stars. So either the temperature of both has to be the same, or the luminosity of both has to be the same. In a blackbody spectrum, it doesn't directly give you size. You have to infer relative size based upon the blackbody curve using this relationship. So typically when you're given a problem like this, either the temperature is the same for both or the luminosity is the same for both. It's really hard to establish which star is bigger when both the luminosity and temperature is different for both, because then it depends upon the ratio of the luminosity and temperature. So you'd actually have to calculate in that case.